Okay, welcome to this series lectures about stellar atmospheres. It's going to be just an overview because we have some 9 lessons about that, and the topic is huge. Actually, there are places where they give PhD courses entirely only on stellar atmosphere. So the topic is very extensive. And we have just 9 lessons, the time to fix the main concepts, to find, starting from what stellar atmospheres are and why they are important, and then the basic concept and equations and the problems related with with this topic. It's going to be just the idea is an overview because we do not have the time to go into all the details of this very extensive topic. Now, while the 9 lessons will be some not enough details for full preparation, we start from an introduction to this introduction, in the sense, as I used to do in my courses, and the first point I think is important to get is the concept about the topic, what we are studying, why they are so important, that people teaches entire courses only on that, why it is so important, why it is so hard, so difficult, the point, so elaborated, and also starting from what stellar atmospheres are, because I think that actually it's not an easy concept. I think that at the beginning, when someone, particular student, starts thinking about stellar atmospheres, it sounds like something very exotic, because I think we know very well what an atmosphere are in the case of a planet. But for us, because in the planet you have a rocky planet, you have a rock solid and gas, a gaseous atmosphere around, and it's easy to understand it. You think about our Earth, and this is simple. But when you start thinking about a star that is actually gas, it's not clear why it should have some atmospheres around. A sphere of gas with an atmosphere of gas around. What's the concept? What's the point? And also it's not clear why they are so important in stellar astrophysics. So we start with this, trying to catch the concept itself of what stellar atmospheres are and why they are so important. So, and I would like to draw your attention about something that maybe you thought about that, but maybe not. Think about the sun. You know, because hereafter I will assume that you have seen in this course the basic equations of stellar structure, and then how the stellar interiors and all the, for example, hydrodynamic equilibrium and so on. So I assume you have the concept about stellar structure, the equations of stellar structure, convection, radiation, and so on, and how the structure of the star can be. And so you should know that you expect the star to be a sphere of gas, plasma, let's say, with density growing toward the interior. So you have the maximum density at the center of the stars, and then the density decreases outside. And you can imagine, it's not so simple, but you can imagine there is a surface where the star ends. It's not so easy, but you can imagine something like that. Okay, but if the star is this way, if you look the star, you would expect to see the sun, for example. As the density increases inward, you should expect to see very blurred edges, because over there you have density 0 or very low, and then start increasing, and with this increase of the density, the star becomes more and more bright, more luminous, becomes brighter and brighter. So you should see a very blurred star because there is no sharp edge, there is no sharp surface, and you say outside you have no star and inside you have the star. The density does not decrease suddenly to zero so that you can identify a surface, a limit surface. No, the density is a continuous function, so you should see a continuum edge increasing. This is what you would expect from this concept of how the star is a sphere with a density varying with radius and not dropping to zero suddenly. But if you look at the sun, this is not what you see. What you see is a very, very sharp disk with an edge very well defined. So the first point, when you compare the expectation with the reality, you say, why I see the star, why I see the sun, and any star actually with a so sharp, so clear edge, and not a decreasing, as if there is a region where there is a star, and there is a region with no star, zero density, as if the density drops to zero suddenly. And here, if you think about that, you start thinking about stellar atmospheres. This is the basic concept of stellar atmospheres. This is why I start from here. To understand this, we can think about a planet that is easier, but conceptually is very simple. Actually, this is why we use the same term, because we say stellar atmospheres exactly as the Earth atmosphere or the atmosphere of a planet. So we can start thinking about a planet. And in the case of the planet, it's easy because you have a solid matter, a solid sphere, a rock, and a gaseous atmosphere. So the difference is clear. And if you look from outside, you look at the planet, you cannot see inside. There are a lot of matter inside the planet, but you can never see that. You can only see the surface of the planet. But there is an atmosphere, but you see through the atmosphere. So you have an atmosphere that you can consider more or less transparent, and you see through the atmosphere down to the surface, to the last in the sense of going outward, the last surface of the rocky part. And you cannot see, your line of sight cannot go through this last surface. Actually, it is not exactly that, because if you take this is, for example, the spectrum of the Earth taken from above, from space, more or less at the Sahara Desert. There, the temperature is 320 Kelvin, more or less. And if you look from outside down to this region, okay, it's here, the Sahara Desert, you would expect to see more or less a black body with a temperature of the emission of a black body with temperature 320. And this is because you have the solid rock that is heated by the sun, of course, so absorbs the radiation from the sun, keeps a certain temperature, and emits as a black body, more or less. But this is not exactly what you see. You see that, yes, there is something that resembles a black body at 320 Kelvin, but superimposed to that, there are huge, well, this is in the infrared, of course, there are huge regions of absorption by molecules, water, ozone, CO2, and so on. So there is a continuum that is a black body that you would have expected, but a lot of absorption. This absorption is not by the Earth, by the solid Earth, it's by the atmosphere. So the light comes from the surface, the solid surface, but goes through the atmosphere and changes. And it is, in this case, it is absorbed at certain wavelength because of molecular bands. If you do the same, but at other wavelength, possibly in the optical, you will see much less absorption, but you will see something. And you will see also some lines in emission, because the upper atmosphere emits at some certain wavelengths, let's say. So the spectrum of the Earth would be a black body with molecular absorption, atomic atomic emission also, all together. So resuming what you see at the Earth, what do you see? You see the light emitted by the last surface of the solid rock changed by the atmosphere, because this light emitted goes through the atmosphere and it is altered, it is changed. And from outside, you see this effect. And your eyes do not see inside the solid rock, never. What you can see only is the light that comes from the surface. Okay. Why this? Because in physics, you can say that solid rock is an optically thick material, that is something that do not let the light go through. So if inside the Earth a photon is emitted, it does not escape from that because it is reabsorbed over there. It cannot escape. But on the surface, if a photon is emitted, it goes away. So the solid rock is optically thick. This means the radiation cannot go freely through it. So this is why you cannot see. If you cannot see, it means that the radiation emitted over there does not reach you. But the radiation emitted on the last surface, yes, it's free to reach you, but has to interact with the atmosphere. Now, if with this in mind, we go to a star, we see exactly the same, because we have mentioned before, you have density increasing inside. So inside the star, there must be a very high density. This means, because of the high density, that the material is optically thick. And this means that the radiation cannot escape freely. It's very instantly reabsorbed. So this means that the radiation emitted by the core or by the internal regions does a very short path before being absorbed again, and then emitted, and then absorbed again, and then emitted and absorbed again. So what happens over there cannot reach your eyes. You cannot see that because everything that is emitted there is reabsorbed, cannot escape, and cannot reach you. But density decreases and decreases. So outside, you must imagine, surely you imagine there must be a region of so low density that the radiation is free to go through it, even if not completely free, because part of this radiation will be absorbed or will interact with this matter. But the density over there in some outer layer will be so low that at least part of the radiation can escape, and the other one no, because of a matter of density. But if you have density increasing inward and you have optically thick region inside that you can see, and the optically thin outside that is semi-transparent or transparent, there must be a transition region. And this is exactly what happens in a planet. In the star, you have the optically thick region that acts as the rocky part of the planet, and an optically thin region, layer outside, that is lower density, has a lower density, so the radiation is transparent or semi-transparent to radiation, and the radiation can escape from that, but not completely freely, because in that atmosphere, still the matter can interact with light. So there will be absorption in bands, in lines, emission in lines, exactly with the same as it happens with the atmosphere. That is not totally neutral. The radiation that comes from the surface of the Earth does not escape freely from the atmosphere. And it's clear here that it's not free, because depending on wavelength. Well, in a star it's the same. Now, the only point that we will investigate much better later in this course is that the transition region, for many reasons that we will see, is extremely thin. So in a star, you pass rather suddenly from a region optically thick that you cannot see and a layer outside that is optically thin. And so and this is why you have something like an abrupt change. And this is why when you look at the sun, what you see actually is a disk that you can consider the last last in the radial sense, the last optically thin layer. Inside that surface you cannot see, but outside it's transparent, and this is why you see a sharp edge of the star, even if the density does not sharply goes to zero. So the effect we were commenting here is not because of density, it's because of the interaction between the matter and the light. What happens is that density continuously decreases, but the interaction between the matter and the light jumps very quickly from an optically thick to optically thin regime, and you have a sharp edge. Actually, to give number in the sun, more or less, you know the radius of the sun is 700,000 kilometers, and the atmosphere, that is the region of optically thin above the last optically thick layer, is some hundred of kilometers, 300, 500 most. That is much less than 700,000, that is the radius. So you have a sphere optically thick and a very thin layer of atmosphere that is optically thin. And this is why we have a well-defined surface. Now, resuming what we were, the basic concept, the fundamental concept we have just seen is not only, okay, that you have a sharp edge of the star. We have mentioned more about this, more concepts that are important. The first one is that then all you see from the star is radiation, because remember that in astrophysics, what you receive from the stars, from your objects, are actually almost only radiation. I say almost only because in the last decades, neutrinos and gravitational waves have opened new windows, but mainly they are still emergent parts of the astrophysics. And before it was only radiation, now it's still mainly radiation. So the information you receive from the objects, in particular from the star, is almost only radiation, but that radiation does not come from anywhere in the star, but only from the atmosphere, because any radiation generated inside is reabsorbed, does not reach you. So if you can imagine that a certain layer in the star is emitting, let's say, so to speak, as a black body of 1 million Kelvin, you will never see from the star the emission of a black body from a one, because that radiation is reabsorbed, and you will never see that. This is not the energy. The energy you see is the energy that comes from the inside, but it's transformed during the path. So you see the energy is transported from the inside outside through radiation, but the radiation changes, and all the radiation you see from a star is formed only in the last layers that are the stellar atmospheres. It is impressive to think that all you see is only what is generated in this very, very thin layer compared to the radius of the star. So you have hundreds of thousands of kilometers that you cannot peer through, and what you see only are the last few hundred of kilometers. And there, the radiation is formed, all the radiation with its continuum, with its lines. When you talk about the spectrum, for example, of a very cool star, or star like the sun, or a very hot star, all these spectral energy distributed is always and only stellar atmospheres, is formed only in the stellar atmospheres. And as I will mention you, this radiation that is from there is the way that the energy generated inside the nucleus is transported. So it's a medium of transport of energy. So the energy comes from inside. And I would like to stress, what we see of a star in terms of radiation is only the stellar atmospheres. And this is a concept that when you study stars, you must never forget, because I will make you some example. For example, when you make measurements of in the spectrum of the star to derive the chemical composition, for example, of the star, it's not the chemical composition of the star, it's the chemical composition of the stellar atmospheres, because this radiation we are measuring comes from there. And you can assume sometimes, but sometimes you can't, that the composition of the stellar atmosphere is the same as the layers below, as the stellar interior. And there are many cases. For example, if you have a look at the horizontal branch, hot horizontal branch star, you see, this is, for example, in globular cluster M13, and you see that up to a certain temperature of the stars in the horizontal branch, the quantity of iron, for example, is low because it's a globular cluster, a metal pool globular cluster. Beyond a certain temperature, suddenly jumps to a solar value, actually. So as if the star is a solar metallicity. Makes no sense, because the stars belong to a globular cluster that is metal pool. Makes no sense that they are solar metallicity. This is why. This is because in these kind of stars, and this is replicated also in all the other elements, well, magnesium seems not, but chromium and titanium, the majority of heavy elements. This is only because in this kind of stars, for very complex reason, actually not fully understood, at a certain temperature of these stars, some mechanism of atomic diffusion start, and this make that in this star the light element drop down, they are sink down, and the light the heavy elements are pushed by radiation pressure toward outside. So you end up with a metal rich atmosphere and a metal poor interior, but what you see is only the atmosphere. So you cannot see that inside the star is metal poor. You can only see the radiation from the atmosphere, where you see plenty of lines and you measure very high metallicity, while the star is not by itself globally metal rich. And this is why important for you always to remember that what you measure is only the stellar atmosphere, because sometimes the stellar atmosphere, so to speak, lies about what the star really is. The same happens along the giant branch. This is, you see a sequence, evolutionary sequence from main sequence to lower giant branch, upper giant branch. See, for example, what happens in the same cluster. So you have stars of the same age, the same chemical composition, and look what happens, for example, to lithium. Lithium is high and then starts to drop as you go up in the giant branch. But these are the same stars that formed in the same globular cluster, and they are expected to be formed from the same chemical composition. Well, today it's more complex than that, but we can suppose why as the stars are evolved in the upper giant branch, the lithium decreases. And this is again for the same reason, because lithium in a star is burned. Lithium is very fragile, so it's burned very easily, and lithium in a star is quickly burned inside because it's too hot for lithium, and so it's quickly burned. So inside the star is poor of lithium, but outside in the atmosphere, the temperature is not so high, so lithium is preserved and is there. So in a main sequence stars, when you see that lithium is high, it's actually high only in the atmosphere, only in the outer layers, because inside lithium has been burned. There is no lithium actually in a star, in a main sequence star. So you measure lithium, but only in the surface. Then when the star evolves along the giant branch, there happens some mixing phenomena that mix the atmosphere outside with layer below. And so the lithium-rich part outside is mixed with a lithium-poor side inside. And so this means that the quantity of lithium that you see outside decreases because of this mix. And this is what you see, that as the star evolves along their giant branch, the lithium decreases. Something similar happens for carbonium, for nitrogen, carbon, nitrogen, for example. And this is an effect of what I think you know, the CNO cycle. When you burn hydrogen through the CNO cycle, you alter the quantity of carbon with respect to nitrogen and possibly oxygen también. This happens inside, only inside. So in the surface, you do not see anything. But when the star mixes, you dredge up from the interior material that is altering its chemical composition. And so you start dredging up from the interior material that is poorer in carbon and richer in nitrogen. This is not a star that is changing its global chemical composition globally. It's just a mixing effect that dredges up to your eyes what is below. Okay, these are just some examples that it's important, because you should always keep the warning that when you study a star, you only study the stellar atmospheres, and it's not necessarily the same in the interior. So it's not, the star can be very different inside and outside. There are cases like this. Okay. Now, starting from this, I hope that these have given you an idea of what stellar atmospheres are, why we talk about stellar atmospheres, and also why they are so important. Actually, I was mentioning before, there are entire courses, PhD courses, only on stellar atmospheres, because it's there that the radiation that you see is formed. So if you want to study the spectrum of a star, or even in general, the energy distribution of a star, you need to know well the stellar atmospheres, because the radiation you study comes from there. So this is why stellar atmospheres are a key part of the structure, but also of the observation of stars. Now, I would give a very rough and rapid overview of what the study of stellar atmosphere is. We will return then better with during these 9 lessons, of course. This is just a rapid overview to have an idea of where the field we are entering, what's the topic about. If you study stellar atmospheres, you must study stellar atmospheres, for example, because you need, for example, to interpret the spectrum of a star. If you want to transform these lines in a chemical composition, a chemical abundance of some elements, you need to know the physical, for example, the physical parameters, the physical conditions of the layers where these lines are formed. That is the atmosphere, the temperature, the pressure, and so on. So if you want to study the spectrum of a star, you need the theory of stellar atmosphere. So the first point would be to define the structure of the stellar atmosphere. This is, in theory, what you already know, more or less, because I think I assume you've seen about the stellar interiors and the equations. And what's the point over there? You take all the equations of you take all the equations of the stellar structure to solve them and to build a model. And the model is a series of layers from, for example, from inside to outside, where in each layer of the model, you have the physical conditions that are the variables of the system you are solving. When you put all together the equations of stellar structure, and you solve that to get the variables in any of the various layers that you are modeling. Now, for the stellar model atmosphere, you first need something like that, a model of the atmosphere. That is, again, a model that is a series of layers. For example, this is, okay, it's cut because only a part, but it's part of a model of 72 layers. Each layer is a line which gives the physical conditions of that layer. That is, in this case, density, temperature, in Kelvin, of course, pressure of the gas, and pressure of the electron pressure. So for every layer, you have this physical condition. This means in every layer of these models for the atmosphere, I have the physical condition of the matter over the density, temperature, and pressure. Okay. How do you get that? Well, in theory, you could say, and this is what you can read about a great book, the Kippenan. This is very instructive, I think, what Kippenan writes in his book. Because the concept is, okay, you can do the same as you did for the stellar interiors, in theory. Because in the stellar interiors, you do exactly the same, no? You do exactly the same. You build a model solving the equations, hydrodynamic equilibrium, convection, radiative transport, equation of state, nuclear reactions, and whatever. You put all together, and you solve the question, and you have the model. You could do the same for stellar atmospheres, but with one difference. That is huge, because makes the things much, much harder. The difference is that in the stellar interior, you approximate the transport of energy through radiation with a diffusion model, with diffusion equations that are pretty simple. I assume you saw that you in the series of equation of the structure, you assume the radiative transport, but the radiative transport is diffusion. And it's obvious because the diffusion. Why? Because from one layer to the other, all the photons that are emitted are constantly absorbed and emitted again, and absorbed and emitted again. And so you have a process, a physics process that is very, very similar to diffusion. A diffusion of photons, a diffusion of energy. Okay, easy. But in the stellar atmosphere, this is not valid anymore, because in stellar atmosphere, the matter is not optically thick. So you cannot assume that the photons are just constantly, layer by layer, absorbed and emitted and absorbed and emitted. No, the photon can escape because the matter is optically thin. So you cannot use such a simple equation as before. So you can do something very similar to the stellar interiors, but over there you must substitute the diffusion equation for radiative transport, and you have to consider the interaction between matter and radiation, step by step. And you have actually to use the complicated full set of transport equation for radiation. Okay, why complicated? Because in this case, when it is diffusion, as here, it's easy because, okay, all the photons are absorbed. When you start doing step by step, you have to consider, for example, wavelength. Because if there is an atomic line, the absorption is higher. So the probability that a photon escapes is much lower than in absence of a photon with the wavelength of an hydrogen line is very hardly will survive. It will be more probably absorbed because there is a lot of hydrogen in its path. But it depends, because if there is a lot of hydrogen, but it is, for example, ionized, it doesn't matter. The photon will be free. So you have to consider the state of ionization and of excitation of all the species, atomic species, to consider how many photons can escape from there and how many are absorbed step by step. And this, for example, the ionization and excitation state of all the elements depend on the physical parameter. So this will be different layer by layer. So you have to integrate the equation considering that changing the parameter, the interaction between radiation and matter changes. And so you have to consider all the possible transition. That is not only lines, it can also be a bound free or scattering, free scattering of free electrons, and all the possible combination between matter and radiation. And you have to integrate them step by step, because this changes the flux of matter or of radiation, and the flux of radiation also alters potentially the physical condition. Because if I have a layer, for example, that is very optically thick, for example, that leaves very few radiation to go through, it will be heated because it is absorbing energy. So it will get heated. So it will temperature will grow. So the interaction between radiation and matter also alters the physical condition. So you have to solve all these equations. And if you have seen that solving the equation of stellar interior is hard, for the stellar atmosphere is harder, because the equations are much more complicated. Okay? When you have this model, supposing you have this created this model atmospheres you can at this time integrate the equation of radiative transport along the model, because once you have the model, you can take all the wavelength one by one and integrate to see what comes out. I mean, I throw 100 photons of this wavelength at the bottom of the atmosphere. They go through the atmosphere. I integrate the equation to see if they are absorbed or not, and how many get out on the other side. And if I do for many different wavelengths, what I get at the end is a spectrum, a synthetic spectrum, because for every wavelength I see how many photons are absorbed and are emitted throughout the atmosphere, and I generate a spectrum. But for that, I need the details, the atomic details of the lines and the transition I'm considering. Because if, for example, I'm considering photons of a certain wavelength, that is exactly the wavelength of some transitions, for example, some atomic transition, okay, depending, I need to know these atoms, for example, I don't know, iron or whatever, these species of atom, how they are, if they are ionized, how much they are ionized, the state of ionization and excitation in every of these steps. Because of course, it can happen, for example, that in the lower layers, it's too hot, this species is ionized, so my photon goes through because there are no atoms able to absorb it because they are all ionized. But when I get at the end, the matter is much cooler and they can be absorbed. So you need, and for this, you also need, it's an interaction between the atom and the photons. And to specify that, you need to know the probability of transition. If this atom, if this photon meets an atom, is it absorbed or not? It's a matter of probability. So you need the model. So you need, for example, often, depending, this is an overview, I'm trying to, I repeat, it's not very, very precise what I'm saying, but just an overview, an idea. You often can need a model of the atom. This is, for example, a model atom of iron 4 times ionized, and you see that you have various levels with an energy. So each of these points are different levels that actually are identified here, and each line connecting one level to the other is a line, is an atomic line. All these are atomic lines that are all the possible combination of transition between one electronic level to the other one. And with all this, with the model of an atom, you can build the possible lines and calculate the wavelengths and the probability of interaction. Because I don't know how much you know about quantum physics, but in brief, the fact that you have one level and the other level doesn't mean that there is a line, and it doesn't mean that there is a line that probably you will see. It depends on many factors. Some lines cannot exist because they are forbidden, for example, and some other lines can exist but will be very weak because the probability of this transition is very low. This depends on quantum parameters of the atom. So when you build the model of an atom, you can actually model which lines are important, which one will be very weak. You will never see in the spectrum of a star all the iron lines, for example, all with the same strength. There are some that are very strong and some that are extremely weak, or actually you cannot see them. Why? Because there is a matter also of probability of the transition. So you have to also to model not only, so you see that you must model the matter as in the stereo interiors, but you need to know the interaction between matter and radiation. So all the possibility of radiation, of interaction between radiation and matter. And then you also have to know, to know this, you also have to know the structure usually of the atom, some way to know each line, the parameters of the line that you need, because this parameter here, each one is a line with wavelength and parameters, that is excitation potential and logarithm of the oscillator strange is here, logarithm of the oscillator strange. That is in fundamental parameters, because this tells you how strong is the line or not, but depends also of the physical condition of the model. So you need this atomic parameter for the line to model if the lines are strong or not, and eventually depends on how many iron is there. But a weak iron line doesn't mean that there is no iron, because it depends also if the line should be strong depending on its parameters. So you have to govern all these to eventually obtain something like, for example, a synthetic spectrum. And with the synthetic spectrum that includes both the lines and the continuum, so also the emission and the emission in the continuum, with this you can compare with the observed and measure the temperature of the star, the surface gravity that also tells you the evolutionary state of the star, then the chemical composition, the abundances of the various species. Okay, and so if you want to interpret a spectrum that you receive from a star, you need to compare it with expectation, with models, one way or the other. You must have some expectation behind, some calculation behind, and you need all this. And this is why, as I was saying, this is on one side very important, because if you do not have studies of stellar atmosphere, you receive a spectrum from the star, you see, nice, good, very nice, and you cannot do nothing with that. You cannot do anything with that, because if you want to interpret the spectrum, the observed one, you need the study of stellar atmosphere. And on the other side, it is also very complicated, let's say. So this is why it's something huge, that it's an important topic with a lot of things. There are entire books about stellar atmosphere, but it's fundamental to interpret the star and to study the stars. Now, the first step of our lessons, we will, okay, this is the end of the overview. I hope it was useful to understand what we are going to understand what's the topic and what, because I consider that if we start here defining things and throwing a question, you could have no idea where are we going, why are we doing that. So this is why I gave you this introduction, to have an idea. Forgive me if I was not precise everything. I try always to to favor comprehension and clarity with respect to rigorousness, to say exactly the things as they are. So sometimes I was not too rigorous in what I said, but the idea was, okay, to go give an overview that can, in this way, in the next lessons where we'll see things, you will start to have an idea why, what are we doing, where do you want to get, what do you want to get, what is the object. This was the idea. Now we start, and starting, I would need to start from defining a series of quantity, because there are a lot of quantities that will be the basis of our work. No, okay. There are some various quantities that you probably already know. I expect that you probably already know, but good to repeat if it's not something, if it is nothing new. It's good to repeat, because we need to have very clear ideas about what these are. The first quantity we define is the specific intensity. That is sometimes also called surface brightness, and it is, we can define it from this equation, considering that the E is the amount of energy transported through the surface A in the time, the T, in the frequency, the nu, and in the solid angle omega. So this is the total energy coming from there, and it is proportional to the area, to the solid angle, to the interval of frequency, and to the time of emission. And the, let's say, quantity of proportionality is the specific intensity. So you can say that specific intensity, as the energy here must be energy, and in TGS it will be erg. This must be erg for unit area, unit solid angle, unit frequency, and unit time. So it will be erg in centimeters -2, and so on. So you can consider specific intensity as the energy emitted by this quantity of area per unit area, per unit solid angle, per unit frequency interval, and in a unit time. And we can also define, and will be sometimes be useful, the mean intensity, that is just the average in all the direction, because the mean specific intensity is a function of the solid angle. This, we will see, I think we will see very soon why we define it as a function of solid angle, and it is very, very useful to do that. We will see it later. But if you want the mean, but if you can, of course, you can suppose that this tiny area is emitting energy, not the same energy in all the directions. Sometimes yes, and in that case we talk about isotropic emission, but sometimes it no. Usually no, actually. So this is why we give the emission as a function of the solid angle. And sometimes you can also prefer to have the mean value integrated, averaged over all the direction. And this is the mean intensity. Just one point. Here I will very, very easily and frequently in these slides switch from a notation as a function of frequency and as a function of wavelength. I will not complicate much, just to switch in between one and the other whenever needed, depending on the notation, what is easiest to do, but okay. It is easy because, of course, you know, if you have intensity in frequency, you can just multiply for a constant and light speed and the wavelength, and you have the equivalent in wavelength. So I will just switch from one to the other without saying that, okay? Because I will just say in any equation, this can be frequency or wavelength, depending on the situation, and I will not complicate much on that. Now, this is why I was saying that it's very common to have a quantity that depends on the solid angle. This is a very easy as an exercise. I will not stress too much step by step, because you have the presentation, you have this PowerPoint, You have this lesson recorded, so I invite you just to check this equation and to check the result. It's very, very easy. What's the point? Suppose an emitter, an area emitting and an area receiving, and you calculate the energy emitted by the area, by the emitter, that goes through the receiver, and the energy received by the receiver that was emitted by the emitter. And they must be equal, because of course, they are the same quantity, as seen from the different point of view, but they are the same quantity, so they must be equal. But the solid angle is not the same, because the emitter, in one case, you use the solid angle, the omega, that is the solid angle of the receiver as seen by the emitter. And in the other quantity, you use the omega prime, that is the reverse, the solid angle given by the area of the emitter as seen from the receiver. So these are different. But if you do the calculation of what the solid angle is, that is projected angle divided by distance, and you go through the equations, the fact that the two energies must be, of course, be the same results by the fact that the specific intensity also must be the same. And if you take the receiver and throw it twice as distant or 1,000 as distant, the equations are the same. So this means that the specific intensity does not depend on the distance of the object. So you have a quantity that depends only on the emitter, its physics, its emission, but not the distance to the receiver. That is very useful, because it's very hard sometimes to work with quantities that depend where the receiver is. These are universal quantities that does not depend on the receiver and its position. So this is why the dependence of the definition of the specific intensity as per unit solid angle gives you a quantity that does not depend on the distance of the receiver. And this is very useful. And I also mention here, because we will possibly use it later, no, much later surely, when we will talk about local thermodynamic equilibrium, but maybe something before can be useful, just a mention. It's easy to see, to know, to think that the specific intensity in the case of thermodynamic equilibrium is the Planck function that you must know, of course. The Planck function, that is the emission of a black body. Well, this is very easy. Why? Because in thermodynamic equilibrium, you actually have the emission of the object that is exactly the same energy that is absorbed, because it's thermodynamic equilibrium. So its constant is always the same, and the Planck function is the same quantity. The Planck function is the energy emitted per solid angle, per frequency and area and time, exactly the same. So they coincide in the case of thermodynamic equilibrium. This is very important, because later, whenever we can, and this is the important point, whenever we can approximate the physical condition of the star, of the atmosphere of the star, as if in thermodynamic equilibrium, we know a very well-known expression for the specific intensity, that is its emission. So it's much, much easier. The problem is that thermodynamic equilibrium usually is not, well, formally is never, because a star cannot be in thermodynamic equilibrium, because it releases energy, emits energy, and does not receive energy. So it's losing energy. And this is the opposite of the idea of thermodynamic equilibrium, where everything you receive, you give. The star gives but does not receive, so it's not thermodynamic equilibrium. But this is the star as a whole. The atmosphere could be different. So the atmosphere could be approximated in thermodynamic equilibrium in a good way, possibly. So we must remember this. Another definition is the flux. Radiative, because of course it's flux of radiation. When we talk about flux, it can be a flux of many things. In this case, it's flux of radiation. and monochromatic because it depends on wavelength. This is its definition, very easy. It's the integration of the specific intensity on the solid angle multiplied by the cosine of the angle with respect to the normal of the surface we are considering. And this gives you, integrating in the all the solid angle, the net flow of energy per second through the surface. Okay. Why? Because this is the emission, but goes with solid angle, but also with the direction. And of course, the units, is, if it is integrated per solid angle, and you consider the dimension of the intensity, and you integrate with solid angle, so the dependence of solid angle disappears. Easy. It's energy per second, per area, and per frequency. It is useful, we will do it later, to distinguish in this case between the flux inward and outward, because when we talk about, imagine this, it's useful if you always try to think what we are doing in the context we are doing that. So these are universal definitions that can be used in physics for many things. But here we are not using it for many things. We're using it for stellar atmospheres. And in a stellar atmospheres, the two sides are not the same. Here below, you have the stellar interiors where the flux, the energy comes from. And on the opposite side, you have the universe, the interstellar medium, where the energy will eventually escape. So what enters and what goes away is not the same. It's very different. On one side you have the star, on the other you have the universe, and the difference is not the same. So it's very useful in our context to distinguish between inward and outward flux. One is the flux going toward the stellar interiors, and the other one going outside. And you can say, the first one is, of course, a zero. No, because if you have a thin layer and it absorbs the energy, it absorbs the energy coming from inside, and it emits, for example, for scatter. Just imagine scatter. And part of the flux that is of the energy that is crossing this surface is scattered inward, apart. Not all, because if it was, well, we would have no flux outside. Of course, no. Of course, the net flux, considering all the contribution, is toward outside. The net side. But each layer can also reflect, so to say, scatter part of the energy inward. So there is usually in an atmospheric layer an inward flux. It's not always. What is sure is that if we have isotropic radiation, so this surface is emitting in all directions in the same quantity, of course the flux is zero, because you have inward and outward in the same and in all the directions. So the two contribution from inward and outward cancels out, and you have zero. Okay. And these are some more elaboration about that. Not very hard in this case. Of course, whenever you need to go above the dependence of wavelength, for example, because you need the total energy or something like that, you can integrate on the frequency or the wavelength, and you have the total flux, the total radiative flux. And here we can define the flux emitted by a spherical star that is not irradiated. What does it mean, not irradiated? That there is no incidence flux. The star is emitting outward, but does not receive anything. It is not receiving. You could say this is obvious. Not necessary, because, for example, there are many cases of binary star where one of the two is heated by the companion. If the binary star is very close and you have a very hot star with a companion, the companion usually is heated, receives a lot of flux. from the hot companion. So it is not always the case that star is isolated. But if it is, so it is not irradiated, so it does not receive flux, but it emits. And on the surface, the r, that is the radial, of course, the radial coordinate in spherical coordinates, equals to the radius of the star, because we are on the surface, and we can write this and consider this quantity as the intensity average over this disk and received by a distant observer. If we multiply this by the stellar surface, that is 4p radius, we have the stellar luminosity, but it's a function of the frequency of wavelength. So we call it monochromatic because it depends on the wavelength. And if you integrate over all the frequency, we finally have the total stellar luminosity. That is a quantity that I'm sure you've seen previously in this course, because it's a quantity very useful, used in astrophysics. It's a parameter of the stars, and so I'm pretty sure you know it very well. But it was interesting to link this total stellar luminosity that is very used in astrophysics, you will find it frequently, with the quantity we have just defined. In particular, the flux that you can integrate on a star, and then this is what you obtain is per unit area. So you multiply by the stellar surface to have monochromatic stellar luminosity, and then you have the total luminosity. Okay. This is something very easy. I leave it as an exercise just to go through the equations, because I think we are running out of time, and it's very simple. It's very simple because it's just a way to show you that this that we were mentioning, that is the flux emitted, is not the same as the flux received. And the flux received, the flux observed, that is received by observer, is a quantity that depends on the distance. The flux of a surface area does not depend on distance. When you integrate on the whole star, it depends on the radius, but not the distance. But if you consider here the flux received by the observer, of course, this depends on the distance. In particular, it decreases as the square of the distance. And this is very well known. I'm pretty sure you already know. But it's important to link this with our previous quantities, because actually you see that you can connect the flux received by observer as ratio of the radius and the distance with this quantity that is the same we have just defined here. Okay? You see. Why? Because this is the connection between what you have just defined, that is intrinsic of the star, and it's useful to model the atmosphere, with this quantity that is fundamental for another reason. It's the only thing we measure. When we study a star empirically with observed quantities, we got this flux, nothing of what we've seen before. Actually, not even the luminosity of the star. From measurement, we need the distance for that. So we need to connect the observed quantity with the quantities we are just defining. So check these equations, but it's I'm pretty sure it is very straightforward. Okay, this is another concept. These are other density definitions that can be useful sometimes. No, I think we will use that. It's I don't know if this is the definition of energy density. Now, I would like just to show you the equations are very easy, but how you get that? Because energy density is energy per unit volume and per frequency, of course. That is the energy contained in a volume of the star. So far we have worked with surfaces, but here we have a density of energy in volume. How we get that? Well, you can take, we can use what we have just defined. If you take an area, a very small area, the E, the A, and you consider the in a time the T, the energy that goes through this area, so that crosses this area, and you can consider the volume that this energy that crosses the area occupies after the T. And it's easy to see that as this is radiation, so this this radiation goes with the speed of light. So the volume that occupies is area multiplied by the height, and the height is velocity per time. So it's c the t. So the c the t is the volume, but must be multiplied by the cosine of theta, that is the angle, because of course the volume decreases as you consider a direction of propagation that is not orthogonal. If you consider only the direction orthogonal to the surface, of course the calculation is just area multiplied by the height, and the height is c the t. But if the angle is not 90 degrees, okay, you start having a smaller and smaller volume. So you have to consider cosine. And you have, so you can consider the volume and the energy. And the energy, we already know it. It's the same as before. So the energy, the quantity of energy that passed through this quantity is the same as before. And this occupies a volume that is this. So doing energy divided by volume, you have an energy density. And that's it. That is dividing the energy by the volume, you have this. And you find that is also related to the mean intensity that we've seen before. Okay, this can be useful. In thermodynamic equilibrium, we have the same as before, and the total energy density here becomes what you already know. Easy to show, and you already know that, because you know that integrating the energy density, the total energy density integrated in for the wave on the wavelength, in we are integrating the Planck function actually, and you get the Stefan-Boltzmann equation that is proportional to temperature to force. The same is if we want to transform this not in energy, but in photon, because sometimes it's useful not to know, okay, in this volume we have this quantity of erg, of energy, but to say in this volume we have this quantity of photons. This is very useful sometimes, and this is easy because you know that as this energy is energy of radiation, the relation between the energy of radiation and the photons, that it is the energy of each photon. It's enough to divide this by the energy of this photon that is given by the Planck, the Einstein equation, and so you get the equation. That is approximately, if you put the number temperature to 3, you could take this integration. Okay, this, I don't know if this will be useful later. But, okay, what time is it? Okay. One final point that if you see we go through, we have energy. Okay, resuming what we've done so far, we start from definition of specific intensity that gives you the energy that goes through an area depending on the direction, and per unit time, of course, depending on the direction. We saw that this is interesting. Flux and luminosity and the flux received by the observer. Then we give an energy density, but this is the energy containing a volume, or photons, if you want, contain. in a volume. But if you have an energy density, you know this is because in this volume you have photons, and photons transport energy but also momentum. So you can consider the momentum of a photon that from physics, you know a well-known relation, the momentum of a photon is energy divided by the speed of light. So if you have a surface and you have photons going through, you can consider that you also have a flux of momentum. You have a flux of energy, but we have seen it so far, okay? But you have also a flux of momentum. This means through this area, there is a momentum crossing that is transported by photon. And so you can consider the momentum that is crossing the surface A. And from what we already know from this equation and what we have just written, you find an equation. And what you already know from physics, if you have a surface with momentum going through it, you have a pressure on the surface. And the pressure on the surface is actually the force divided by the area, and the force is the change of momentum in time. So the pressure on the surface, because of the radiation, is force divided by area, that is momentum divided by area and time. And we already have all the gradients here to express this radiation pressure as a function of what we already know, that is the intensity. It's just a matter of starting from here, inserting what we have, and then, okay, here you have the intensity, and you come up with an expression of the radiation pressure. And this is useful. This is very useful because consider that radiation pressure is an important, sometimes critical ingredient in the structure of a star and of a stellar atmosphere. Consider, for example, is that if you have a very hot star, you have a very energetic radiation, so a very high intensity, and this means a very high pressure, and this causes winds because the outer layers of a star suffer a very high pressure, radiation pressure, because the radiation is strong and can push matter to get to accelerating it radially outward and generating stellar winds. So the radiation pressure is, in many cases, a very important ingredient in the structure of a star and its atmosphere. And eventually, okay, you know, in case of isotropy, just receiving what we've seen previously, you get very easy expression of the radiation pressure. Okay, so I think that by now I don't know exactly, but I think it's more or less out. We have run out of time, so we leave it here, but next lesson we will continue with this.